Hello kids, today we're going to be looking at section 5.3 on polynomial graphs. What happens when you graph these lovely polynomials? So this is the last section in the unit, and we're going to be talking about things like how many zeros are there. We kind of talked about that before. How many times can it turn? How many times can a polynomial graph turn? We're going to be looking at end behavior, the LEB and the REB, and that'll make sense to you in a couple minutes. So here's section 5.3. So in polynomial graphs, there are going to be no discontinuities. That's your first blank here. Discontinuities. There are no sharp corners. And the domain for any polynomial graph is going to be all real numbers. That's a nice thing, right? We always are talking about domains and ranges. So for this one, the domain anyway is going to be all real numbers. They're always smooth, lovely, curvy type things. They're not with pointy kind of turns. Everything's got to be smooth and flowy. That makes a polynomial graph. And here's some popular ones. The ones that we know. We know that linear ones, they're the ones that are, I might as well toss it down here, y equals mx plus b, a linear graph. They can be any kind of line. Well, we'll be nice. Make it y equals x. Quadratics, they're going to be x squareds, right? They're the ones that are some type of x squared graph. We know what they look like. They are happy parabolas or sad parabolas. But the general x squared graph looks like that. It could be a cubic graph, y equals x cubed. And hopefully you remember that they are squiggles. Squiggles at the origin. And it could be quartic. And quartic graphs are kind of interesting because sometimes they look just like a quadratic, and sometimes they got a little more beef to them. Sometimes they go kind of like a W. I'm going to make my example like a W. And that would be a y to the fourth type graph. If you were just to graph y to the fourth, it would look like the parabola. So I'm not going to put the equation there, but a quartic graph. So the end behavior is what it's doing on the left and what it's doing on the right. So this one has an end behavior, a left end behavior, an LEB. I might as well toss it in my margin. Can you see my, yeah, you can see my margin. LEB is representative of the left end behavior. Oh, B, can I turn that into a B? Yeah, behavior. In other words, what's it doing when I go far to the left? I'm going to put it in limit notation. Ooh, remember limits? I want to know what the limit is as x approaches left, negative infinity. That's my left end behavior. What's it doing far left? This one would be going to negative infinity. If I'm talking right end behavior, REB, my right end behavior, right end behavior. Now I'm talking about the limit as x gets really far to the right. That would be going to positive infinity. So what's it doing to the left and what's it doing to the right? We're going to bring back the old limit notations on this. And here's the story. You've got four situations, and that's what this box is all about your end behavior. If you have a positive leading coefficient or a negative leading coefficient, that helps you determine what it's doing to the left and what it's doing to the right. The other thing that helps you to determine that is if it's an even degree or an odd degree. I'm going to give you examples of all these four things. So if I'm a positive leading coefficient and an even degree, that would be like my graph of y equals x squared. And so what I'm going to do is I'm going to graph it for you. I know we just graphed it up above. He is Mr. Happy Parabola. He has an even degree, 2, and he's positive x squared. He looks like this. So the question is, if I go far to the left, this is my left end behavior. This is my right end behavior. if I go far to the left, what are the y values doing? They're going towards infinity. And so on the left, it goes to infinity. On the right, what does it do? It goes to infinity. And there you go. That's your left-hand behavior, right-hand behavior. But what happens if I get a negative x squared? Y equals, let me come down here, a negative x squared. What does that do to my graph? And hopefully you remember it flips it upside down, right? It's a reflection over the x-axis. And so here he is now. He is not happy. He's an unhappy parabola. And so if I'm looking at his left end behavior and right end behavior, on the left he's going down. He's going to negative infinity. And on the right he's going down to negative infinity again. They didn't give me much room for that, but that's where it is. All right, if I go to an odd degree would be something, oh, you can't see me on my screen, my bad. There you go. If I have an odd degree, that'd be like y equals x cubed. Well, what does that x cubed graph look like? We drew it up above. He's a squiggle. Whoop. So his left end behavior, if I go towards the left, he's going to negative infinity. And if I trace him on the right, he's going to positive infinity. They're different. Where over here with the even functions, they're doing the same thing, left and right. This guy is doing opposites. Those odd guys. If I have a negative x cubed, he's going the other way. He starts like this. His squiggle goes the opposite way. So his left end behavior and right end behavior, let's see. On the left, if I trace him, he goes to infinity. And on the right, if I trace him, he goes to negative infinity. And what's interesting about these polynomials is that this works no matter what the power is or what the leading coefficient is. So in other words, say I had, and I'm just going to write it off to the side here, say I had some great big polynomial and it was a negative 4x to the fifth and yada yada down the line. It has a negative leading coefficient. All right, that's one of these guys. And it has an odd power. That's this guy. It's going to behave exactly the same way. It's going to behave so that on the left it's going to infinity and on the right it's going to negative infinity. And I don't know about the rest of the graph. I don't know what it's doing in the middle. We're going to talk more about the middle in a few minutes. But I know just from the leading coefficient and the whether the power is odd or even, which of these four scenarios it's going to look like. So I could also have something like, what if I had y equals 6x to the 8th? All right, it's got a positive leading coefficient. That's one of these two. And it has an even degree. That's this guy. So no matter what else it's doing, I know that on the far left and on the far right, this guy's going to infinity both ways. And so that's what this whole chart here is talking about. All right, so if I go to the next thing about turning points, this is considered to be a turning point. It's where it turns from decreasing to increasing. It could also change from increasing to decreasing along the way. But turning points, if you look at any polynomial, it has a degree of n. The degree here is 5. The degree here is 8. So n would be 5, n would be 8, whatever it is. The degree of the polynomial has at most n minus 1 turns. So if I am an x squared, 2 minus 1 is 1. It has at most 1 turn. And we know that that's true for, and it's going to work for any polynomial, but think of your quadratic specifically. Let me give you 3 scenarios here, real little pieces. It could have no, actually I probably want this for the next thing. Let me go into the next thing and I'll show you my pictures. A polynomial of degree n has at most n zeros or roots. So if I have a quadratic, if I have a parabola, it could be up here and have no zeros. It doesn't cross the x-axis at all. It could also have 1 0 where it touches at the origin or somewhere else. Or it could have 2. So how many solutions does this guy? This guy has no solutions. This guy has one solution. This guy has two solutions. So the zeros or solutions of a polynomial, it has at most that many. Some of them are going to be real, and some of them are going to be imaginary. We saw that in that last section that we just did. We solved for all sorts of solutions. Some were real and some were imaginary. And then this multiplicity thing's kind of cool. Factor's multiplicity is the number of times the factor occurs within the polynomial. For example, examine this function. The factor x minus 3, that's this guy. X minus 3. How many times does it occur? You don't have any power on that, so it occurs once, has a multiplicity of 1. While the factor x minus 7, x minus 7 has a multiplicity of 8. It occurs 8 times. That's the power on that guy. This x plus 1, he would occur 5 times. All right. That kind of gives you a flavor for the beginning of this. Let's keep going. All right, so even multiplicities. It's interesting because you can tell when that multiplicity happens how it's going to affect the graph. And that's what this last little bit is before we get into looking at some problems. So if there is an even multiplicity, the graph is tangent. I'm going to show you pictures in a second. Tangent to the x-axis at that corresponding 0. And if the graph has an odd multiplicity, if this function group has an odd multiplicity, the graph crosses, truly crosses over the x-axis at that corresponding spot. So what happens is if I've got x minus 7 to the 8th power, that's an even multiplicity because it's an 8. That means that this guy is tangent. So if I take that grouping, x minus 7, set it equal to 0, I get x equals 7. So when x equals 7, it has a tangent to the x-axis. That means the graph goes some kind of, whatever it's doing over here, I don't know, but when it comes to 7, it comes down, it touches it at 7 and turns around. That's tangent. It crosses through it, like it just touches at that one point. That's a tangent picture. That's what it looks like when they say tangent. Where this guy over here, x minus 3, it actually, if I set that grouping equal to 0, x minus 3 equals 0, I get x equals 3. Where x equals 3, it literally will cross through the x-axis, crosses right on over, keeps going. So you see at this point, it keeps going. It crosses from positive to negative. It could cross the other way. It could go from negative to positive. But the fact of the matter is it crosses. It doesn't stop and turn around. This is a stop and turn around. So anytime it's an even multiplicity, it stops and turns around. We call that tangent. And anytime it's an odd multiplicity, it crosses over. And so let's put all this together and see if we can put some graphs together of what this looks like. So here comes number 1. If I'm looking at this, how does the graph behave with relation to the x-axis at x equals 2? What are the real zeros of the function? What is the degree of the function? And describe the end behavior using limit notation. Okay, so let's figure this out. Let's start with B. What it's doing at x equals 2, let's wait and graph it first, and then we can decide what it's doing at x equals 2. So what are the real zeros of the function? They come from setting each of these factor groups equaling to 0. The first thing you've got is a negative 2. And so that negative, we're going to talk about in a minute. But if I take negative 2 and set that equal to 0, that doesn't give me anything. So what are the zeros of this function? The first thing I'd be looking at is what I have factored out. But negative 2 can't equal 0, so I don't care. Go to x plus 1. If I take x plus 1 equals 0, I get x equals negative 1. So at negative 1, I got something going on. Next one is x minus 2 equals 0. I get x equals 2. At 2, I got something going on. At x minus 1 equals 0, I get x equals 1. They're not giving me a whole lot of space for this guy. All right, so what are the real zeros of this? There they are. Now, can I say what it's doing at x equals 2? Maybe not yet. Let's come back. What's the degree of the function? Well, how many x's do you have? I have 1. See how this is being squared? 2, 3. See how this is being cubed? 4, 5, 6. That means that I have a degree of 6 for this one. Let me show you that again. This x is to the first power, so I only have 1 here. X squared, 2 more, that's 3. 3 more gives me 6. Describe the end behavior. If I'm in x to the 6th, that means I have an even degree. And what's my leading coefficient? So I'm going to say it's an even degree. And really I don't care the number of the leading coefficient, I just care if it's positive or negative. I have a negative 2 times 1 times 1 times 1. So I have negative. It's a negative, I'm going to say LC, leading coefficient. Well, what does that mean for us? That means that if I go back and look at what we did on the first page, these guys here, if I have a leading coefficient that is negative, and I have a degree that is even, then I know that the left end behavior goes to negative infinity and the right end behavior goes to negative infinity. So it has a negative leading coefficient and an even degree. That's this scenario right here. So to answer this question, I know it's going to negative infinity on both sides, so they said use limit notation to describe it. So the limit as x approaches negative infinity of my function, whatever it is negative infinity, and the limit as x approaches positive infinity for my function is also negative infinity. And then sketch the graph. All right, well, let's figure it out. If I'm going to negative infinity on this end, whoop, he's got to go this way. So you know what these outer pieces are doing, right? They both have to be going towards negative infinity, and that's what I drew. But how do I know what it looks like in between? So let's think about that. Let's go back to part A. If I have a grouping, and it is, now I'm looking at this whole, this part up here. If it has an even multiplicity, it touches and turns around. If it has an odd multiplicity, then it crosses through. So I'm looking at each of these groups. This one has a first power. That is an odd multiplicity, so at x equals -1, it's going to cross. X minus 2 squared, that has an even multiplicity because of this number right here. So that I know is going to be in x equals 2, it's going to be tangent, turn around. And then I have x minus 1, so x equals 1. It's an odd multiplicity, odd because 3 is odd. That means it's going to cross. So I guess to answer part A, how does the graph behave in relation to the x-axis at 2? You say it's tangent. So let's see if we can do that. At -1, it's going to cross. Oop, crossing, going over, crossing over. But at x equals 1, it's also going to cross. So, all right, I'm going to have to turn around and cross somehow. But at x equals 2, it's tangent. So it's going to turn around and touch it and go back. And so that's my estimation of what this graph would look like, just based off of behaviors for polynomials. So I sketched a possible graph. Is this exact? Absolutely not. But it absolutely should be. It'd be interesting to see. I don't have the ability to show you on Desmos what this actually looks like. But it should be something close to this rendering that we came up with, just based off of the facts of odd and even numbers and positives and negatives. Okay, number 2. Number 2 says factor the function x to the 5th, yada yada, and sketch the graph if f of -2 equals 0. Well, they're telling you one of the places where it crosses the x-axis. Right now, right here, that's a coordinate. They tell me that f of -2 is 0. That's what I've got. Now, I have a few other things up my sleeve that I can do, but we'll talk about them in a minute. So, and one of them is because what's the leading coefficient and what's the highest degree. We can tell what the end behavior is going to do based off of that. But they're telling us this, and they're giving us a clue. We're going to go back to the last section, and we're going to figure out what the rest of this is. See if we can use that to help solve this. So I'm going to use synthetic division. Remember we did that back in the day of last week? All right, so I have a 5, a 4, a 3, a 2, and a 1. I need a number. All right, so take the coefficients. 1, 6, negative 8, negative 96, negative 128, and then a 0 at the end because I don't have a number. And so I'm going to put together what my synthetic division does. Let's see what happens. Drop the 1, gives me negative 2, gives me 4, gives me negative 8, gives me negative 16, gives me 32, gives me negative 64, gives me 128, gives me 0, gives me 0, 0. So I really didn't need that, I guess. So what does that mean that I have? That means, first of all, I know, and I have it on my graph already, that x equals negative 2. That's one of my solutions, one of my zeros. And then from this, the polynomial that comes about, it's an x to the 4th. So this is equivalent to an x to the 4th plus 4x, actually x to the 4th. I'm saying the right thing, right in the wrong thing. X to the 4th plus 4x cubed minus 16x squared minus 64. If I set that equal to 0, maybe I'll be able to find the rest of these little guys. And so what I'm going to do is I look at that and I'm like, ooh, Nelly, how do I factor that? And you say, yo, there's 4 terms, factor by grouping, split it down the middle. So that's what I do. X cubed comes out, x plus 4 is what I'm left with. Over here, if I take a negative 16 out, I get an x. Oh, this was an x here. Negative 16x, right? Ooh. Can I do that? Should I do that? All right, let me try again. We're going to come back to this because you know what? I didn't do the greatest common factor first. So let me start that again. It's going to be very similar. Just hang on. Hang on a second. Hold on. All right, everybody had an x. I need to take the x out. That's going to give me x cubed plus 4x squared minus 16x minus 64. That's better. Which means the x I factored out comes over here to my zeros. That's my x equals 0. And I can just worry about what's in these parentheses, which we just were talking about. So my front end x cubed and 4x squared gives me an x squared that I can take out. X squared means I have an x plus 4. Back end has a negative 16, leaves me with an x plus 4. All right, factor by grouping, I got the common group. X plus 4, x squared minus 16 is what I factored out. They're my other ones. So let me add to my solution list. X equals negative 4 from this guy right here. All right, let me look at this one. X squared minus 16 equals 0. X squared equals 16. X equals plus or minus 4. So I have, adding to my list, x equals 4, x equals negative 4. These are my solutions, my zeros, my x-intercepts, all the same stuff for this function. So let me plot them on here. I got something going on down here at negative 4. I got something going on at 0. I've got something going on at positive 4. 1, 2, 3, 4. Well, what's it doing on the ends? Because that's really the next piece that you like to look at. So if I'm looking at this, this is a positive leading coefficient with an odd power, an odd degree. Because it's a positive, x to the 5th, 5 is an odd number. So what happens when you have a positive leading coefficient and an odd degree? Here's your chart. On the left, it's going to negative infinity, going down. On the right, it's going to positive infinity. So that's what I'm going to put. On the left, it's going to negative infinity, and on the right, it's going to positive infinity. Cool. There it is. But what's it doing in the middle? So So if I look at this, it has a, let me start at -4. At -4, there's 2 of them. So -4 has a multiplicity of 2. It happens twice, right? You've got a repeat of that guy. He happens twice. And if I have an even multiplicity, go to the top of the page, it touches and turns around. There's a tangent there. So when I come up to -4, it touches and turns around. Do you have any other multiplicities going on with this? At +4, there's only one of them. At -2, there's only one of them. At 0, there's only one of them. So they're all crossovers. Cross, cross, cross. And that's my estimated picture of what this function would look like. So check it out. Without Desmos, like if you're on a deserted island and you can't find, you don't have a graphing calculator or Desmos, you can actually graph this function just based off of the multiplicities, the zeros, and the end behaviors. And that's really the idea of the lesson. Number 3, here we go. They give me this one and they say, given the values on the right, identify the following. And you say, okay, I can do that. Are there any local minimum values? Now, minimum values are the y, first of all, they're the y values. And in this case, what's the lowest y value, like the local lowest y value? We know it goes to -infinity. That's not what they're talking about. They're talking about, is there a low value for this one? So, all right, there's a little valley. Here's where my valley is. What's that y value? 1, 2, 3, 4. So I have one at y equals -4. That's a low place. And I have another valley over here. That's a local minimum. And that would be at 1, 2, 3, -2. It's whatever the y value is. So let me put an and here. Y equals -2. They're my 2 low places. Do I have any local maximums where they're going to be, again, it's the y values. This one is your lowest. Or maybe I don't want to say lowest. They're the low y values, the ones that are in the valleys. Maybe that's how I want to say it, is valleys, local minimums or valleys. How do you spell valley? I think that's right, right? Maximums are hills. So if I'm looking at where my hill is, oh, here's a hill. His y value is 0, so this is at y equals 0. There are no other hills. What is the minimum degree? Well, degrees come from, I can tell how many this is by the number of turns. Let's see how many times it turns. How many times it changes from increasing to decreasing. So here I am, I'm increasing to decreasing. There's 1. I'm going to put my finger there. 1, 1. Then I come down here. Then it changes again. Here's 2. Then I come here and it changes again, increasing to decreasing. There's 3. And then it changes again here at, there you go. Now I got 4. So I have 4 turns. Number of turns is 4. Well, the degree is going to be 1 more than that. Remember that the number of turns was n minus 1. That means that the degree would be 1 more than that, or 5. And now here, this is pretty interesting. Write out the possible function, and you're like, how the heck would I know what that function is? That's a crazy looking graph, right? Well, it all depends on where the zeros are. So figure out where your zeros are, where your solutions are, where your x-intercepts are. The first one I have is 1, 2, 3, 4, 5, 6. I have one at -6. I have another one at 0. And I have another one at 1, 2, 3, 4, 5. And then I want to determine, are they tangent or are they crossovers? So this one is a tangent. I'm going to put a big T there for tangent. This guy is a crossover. I'm going to put a C there for crosses. 5 is another crossover. So these 2 powers must be odd, and this power has to be even. This one has to have an even power. This one has to have an odd power. This one has to have an odd power. How do I know that? Because of this up here. If it's an even power, it's tangent. If it's an odd power, it crosses over. So that's where I'm getting it from. And they have to add up to be 5. All right, so let's put it together. Hopefully I've got enough room. Almost out of the page here. Y equals, that's my polynomial. If I have x minus 6, that means I must have a grouping, and I'm going to leave a little space. I must have a grouping that is x plus 6, right? That's how you get an x equals negative 6. I must have another grouping that's x minus 5 to get this guy. And if x equals 0, that's just an x that's here. So, if I'm looking at this, I have to have an odd power for this, an odd power for this, and an even power for this. So I can make this x a square. And I'm choosing, I'm picking, I don't care, it doesn't matter, it just has to be even. This guy has to be odd. That would be, you can make it to the first. And this guy has to be something else that's odd. It could be, and it has to be at least a degree of 5, so I'm going to make this guy a cube. Odd power. Now remember that it's the minimum degree has to be 5. It doesn't have to be 5, it just has to be 5 or more. So do I have that? I've got 2, 3, 4, 5, 6. Not sure I'm liking that. Hold on a minute. Let me look again. These two are tangents. Oh, this guy should be an even. My bad. Oops. This is not a crossover. This is a tangent. At 0, see how it touches and turns around? Did you catch that? You probably caught that, and here I am. I need you. This would be an even. That would make this a square. That's better. So I have this guy is a tangent, this guy is a tangent, even, and this guy's a crossover. He's the odd power. So even power, odd power. It has to have a degree of at least 5. This one has a 2, 4, 7. This one has a degree of 7. And that still fits for our left-hand behavior and our right-hand behavior. All right, we're not done yet. Here comes the next thing. This is Descartes' rule of signs. And this is all about, this is not going to be a heavy hitter or a big test question or whatever, but kind of interesting stuff. You can tell by how many times the sign changes how many solutions you're going to get. And that's what Mr. Descartes came up with. Now, he's a great guy. Just some cool facts about him. He lived in the 1600s. Wow, that was a long time ago. He's the guy, and you might have heard this quote. This is for my English folk, you know, my folks that like the English topics and literature. He's the guy that wrote, "I think, therefore I am." Anybody hear that? Therefore I am. Kind of cool. He's the guy, that's a popular quote. He is came up with the Cartesian coordinate system. In other words, he's the guy that came up with like your XY axis. How to graph points, how to graph lines. He came up with that coordinate system. And he's considered to be the father of analytic geometry. He's a big dog. He was a big math guy in his world. So here's what he said. The number of positive real zeros equals the number of changes in the sign of the coefficients of f of x. And the number of negative real zeros is equal to the number of changes in the signs of the coefficient of f of negative x. Now it can be less than these when we come out with these numbers. But let me show you in an example. It's probably easier to see in an example. So if I look at this first one, I'm looking at how many times does the sign change. So I go down the line here. I'm talking positive to negative. So I've got, first of all, it goes from 2x to the 6th to a negative 3x to the 5th. So that gives me a sign change, right? So I've got a sign change here. Then it goes a negative to a positive. I get another sign change. Then it goes from positive to negative. I get another sign change. And then it goes negative to negative. That's not a sign change. And then it goes negative to negative again. That's not a sign change. So the sign changes 3 times. So when I look at that, I've got 3 sign changes. That tells me about the positive. That means that the possible number of positive zeros is 3, or it doesn't do evens, it just does odd numbers. 3 or 1, maybe I want to use ors instead of commas. 3 or 1 or none. And then the next thing I want to check to figure out how many negative zeros it is, I need to look at what happens if I put a negative x into this thing. So I want to figure out what f of negative x is. And that's going to make me have a negative x into this. Now, so it's going to be 2 times negative x to the 6th minus 3 times negative x to the 5th plus 7 times negative x to the 4th minus a negative x squared minus 2 times, oh, I'm going to my territory here, 2 times negative x and then minus 11. Let me clean it up and check it out. Anything to an even power goes positive, so this is a 2x to the 6th. This one's going to be a negative x to the 5th, so it makes this a plus 3x to the 5th. This is going to be to an even power, so it's plus 7x to the 4th. This one is a square, so it's going to be x squared, so minus x squared. This one is negative 2 times negative x, so plus 2x, and then minus 11. How many sign changes do I have? And so I'm going to just change my color so you can see them. This was positive, positive. Okay, didn't change. Positive, positive, didn't change. Positive to negative, woohoo, there I go. There's one. Negative to positive, there's another one. Positive to negative, there's another one. So how many sign changes did I get? I got 3 sign changes again. So the possible negative zeros are 3 or 1 or 0. Now, are they always going to be the same? And the answer is nope. No, they're not. All right, skills review we are not doing. You can put a big old X through that. And we're going to pick and choose some of these numbers for the practice problems. So the first one that I think I want to look at, let's do number 3. Okay, they say, determine the possible numbers of positive and negative real zeros. This is old Descartes' rule. And so currently, if I look at the sign changes, it goes positive to negative, negative to negative, negative to positive. I have 2 sign changes. So I have 2 or 0 positive zeros. If I want to know how many negative zeros, I put a negative x in, negative x cubed, minus 7 times negative x squared, minus a negative x plus 15. When I simplify that across the board here, I get negative x cubed. I get a x squared that's positive, so negative 7x squared, negative negative plus x, and minus 15. Let me check how many sign changes I have. Negative to negative, nope. Negative to positive, yup. Positive to negative, yup. Actually, this guy was a plus 15. I wrote it wrong. Whew, get on it, winner. Let me try again. Negative, negative, nope. Negative to positive is yes, that's 1. Positive to positive is not, so this is a 1 or none. So that's how to tell those. Those are relatively easy. It's just counting up the numbers. If I look at the second page, practice problems, let's look at, they're kind of all very similar. They're the same question. Let's do number 6. I'm looking at the graphs, and this one tends to be the biggest, the one with lots of stuff going on. All right, so I'm coming down the line here, and I'm very happy they have it factored for me, because if it wasn't factored, then I would have to figure all this stuff out. So how does the graph behave with relation to the x-axis at x equals 6? So I go to x equals 6. That would be this grouping right here. He has an even power. And so that is asking you, is it tangent or is it a crossover? And so the first thing I know is that because 6 is an even number, and it's the power of 6, then I know that it's going to be tangent at x equals 6. And actually, before we even move on, well, it's the next question anyway. What are the zeros of the function? So check out your factor groupings. You have a 3x squared that's factored out. When I take Mr. 3x squared and set him equal to 0, I get x equals 0. So he's going to be one of my zeros, x equals 0. The next grouping, 2x plus 4 equals 0. What will x be? X will be a negative 2. When I come to the next one, x minus 6, I get x equals 6. And then the last one, x minus 3, gives me x equals 3. So I can put them all across my x-axis. I've got a 0 guy, I got a negative 2 guy, I got a 6 guy, 1, 2, 3, 4, 5, 6. And I have a 3 guy. Well, the degree of the function, let's count up how many x's I've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The degree is 12. Describe the end behavior using limit notation. So I'm going to take the limit as x approaches negative infinity for my function. I'm going to call it f of x so I don't have to write the whole thing out. And then I want to know what's it doing on the right. Limit as x approaches infinity for my function as I go to the right. Well, if I have a degree of 12, that's an even number, and I have a leading coefficient that's positive, there's nothing in here that's going to make that anything else, then I've got a positive leading coefficient and an even degree. If you go to the very beginning of the notes, that means it's going to positive infinity on the left and positive infinity on the right. So I got my end behaviors. There you go. And then I have to determine for the middle of the graph, are these pieces tangent or are they crossovers? So let's go one by one. I'm going to go back up here. X squared, that's my x equals 0 piece, has an even degree to it, an even power there. So that means that in this case, it's going to be a tangent. So the first one I know, this guy's tangent, so I'm going to put a big T by x equals 0, because that's a tangent. Next grouping I go to, where it's negative 2, that has a power of 1. This guy's a crossover. If I come to 6, he has an even power to him, this 6 that happens to be there too, he's going to be tangent. And then I have a 3, he's an odd number, that's going to be a crossover. So let's see if we can do this. Negative 2 is a tangent. Oop, come to negative 2, turn back around. Come to 0, that's the next thing I come to, crossover. Come to 3, that's a crossover as well. Crossover. And then come to 6, and it's going to be tangent. And so that's what my graph looks like. Now these hills and valleys in between here, they could be spikier than what I've got, and it doesn't really much matter. Again, these valleys here, this could come way lower than what I made it, or even a little bit lower, not as big as what I made it. But either way. All right, so let's see. We've got, I didn't finish this out. This is a positive infinity on either end. Sketch the possible graph, and we did. And so that, my friends, is number 6. So let's take it one more. We'll do one more together and see where that takes us. Maybe 2. Let's see where it goes. Number 8 is the harder of these next two. Number 7 and 8. Let me do the hard one. This one, they say the factor of the function, yada yada, factor the function, and then sketch the graph of f of negative 3 equals 0. They're telling one of the places that it crosses through the x-axis. It crosses through at negative 3. So 1, 2, 3, here it is. That's this place, negative 3, 0. They're saying, all right, well, figure out the rest of the graph just based off that one point. And you're like, what on earth? How am I supposed to do that? So you're going to use synthetic division. And so we are going to take this guy. We have a sixth power, we have a fifth power, a fourth power, a cube, a square, and then that's it. So we're going to put those places in and see what happens with this. Outside goes a negative 3. Inside my synthetic division goes a 3, a 4, a negative 42, a negative 36, a 135, oh, 135, not 15, 135, and then I have a 0 for the x and a 0 for the number. We'll put them in there and see what happens. All right, so drop it. 3, negative 9, negative 5, 15, negative 27, 81, 45, that gives me negative 135, 0, 0, 0, 0, 0. The whole back end of that zeroes out. What does that mean you have? And that means you have a 3x to the 5th minus a 5x to the 4th minus a 27x cubed plus a 45x squared. You're going to set that equal to 0 and see if you can factor that thing. The first thing I see is everybody got an x squared, so I can take that x squared out before I get into the next step of factoring. So I get 3x cubed minus 5x squared minus 27x plus 45. And so currently I know I have an x squared equals 0, means that I have x equals 0 twice. It has a multiplicity of 2, right, because of the square. That means if it's a multiplicity of 2, it's going to be tangent at that place. So I know that all those pieces just from that. And now I'm into this parentheses part, and I'm looking at trying to factor that. And so I've got 4 terms, and the only thing that comes up out of my brain is factor by grouping. Let's see if it works. They have an x squared in common. That leaves me with a 3x minus 5. These guys have a 9 in common. It's going to be a minus because this is a subtraction sign. If I take a 9 away, I get a 3x minus 5. Watch your signs on this. Distribute it back. Negative 27, positive 45. That's what I wanted. So factoring by grouping gives me a 3x minus 5 and an x squared minus 9. Set them equal to 0. 3x minus 5 equals 0. X squared minus 9 equals 0. I get x equals, swing the 5 over, divide by 3, 5/3. There's only one of them. He's a crossover. This one, x squared equals 9. Take the square root, plus or minus 3. Those are both individual pieces. They don't repeat. So this one is going to be a crossover for each of those as well. So let's see if we've got it. We have an x equals 0. We have a 5/3. That's like 1 2/3. 1 2/3. Not quite the way to 2. I have a positive 3. Oh, wait a minute. Yeah, positive 3. And I also have a negative 3. Now let's talk about this negative 3 for a minute. Because remember over here, this guy right here, that was also a factor. How many solutions do I currently have? I have 1, 2, 3, 4, 5, and I need 6. So this guy also gives me another solution at negative 3, which means at negative 3 I've got 2 of those. At negative 3, that's going to be a tangent piece. This guy's going to be a t for tangent over here because I've got 2 negative 3s. That's my 6 answers for this guy. So at negative 3 I've got a tangent going on because there's 2 of those. Let's talk end behavior because that's kind of how it's easiest to start graphing it. If I have a leading coefficient that's positive leading coefficient, and an even degree, that's like that very first boxes that we did, that's going to be a going to infinity on either end. Negative 3 is a tangent, comes down, turns around. 0 is a tangent, comes down, turns around. 5/3 is a crossover. Positive 3 is a crossover, and that's my guess as to what this graph would look like. All right, the more I do, the less you have to do. So we'll pick number 10 as my last one. This is it, I promise. Here it goes. Number 10. They give me a graph, and I've got to come up with all these things. So let's see if we can do that. What's the local minimum? All right, I'm looking at the lowest, like the valleys. Where are the valleys? Here's a valley. Here's a valley. What's the y value at the valleys? And they're both the same. They're both at 0. So my minimum, local minimum value is 0. That's the y value at the valley. Maximums are the hills. What are the y values at the hills? Well, I have a hill here. That would be at 2. Maybe I should say y equals 2. I have another hill over here. Well, his hill, the highest he gets to is 3. So I have 2 hills. I have 2 maximum values. The degree comes from the minimum degree, comes from how many turns you've got. Well, this one has 1 turn, 2 turns, 3 turns, 4 turns. So you have 4 turns. That means that the degree is 1 more than that. 4 plus 1 gives me 5. That could be the minimum degree. The minimum degree has to be 5 because that's how many turns I have. And then the last piece is write out a possible function. So if I'm looking at this, I'm looking at the zeros. I want to know what the zeros are. Where does it cross the x-axis? It crosses at 1, 2, 3, 4, negative 4. X equals negative 4. It crosses at 1, touches at 1. And then it crosses again over here at 1, 2, 3, 4, 5, 6. Every place that it crosses or touches the x-axis is where I'm putting my zeros. Now over here it's tangent. This guy was a tangent place. That means that there has to be an even power on this guy. At 1, again, it's tangent. It turns around. So this has to also have an even power. And then 6, it crosses. So 6, it crosses, which means it has to be an odd powered group. So here comes my polynomial, my guess, f of x equals. I have an x plus 4 for this group. I have an x minus 1 for this group. And I have an x minus 6 for this group. Has to be a power that's at least 5. Can be more. Has to be at least 5. This guy has to be even. I'm going to make him a square. This guy has to be even. I'm going to make him a square. This guy has to be odd. I'm just going to make him to the first power. I can pick any numbers I want for those powers. They just have to be even or odd according to what you got going on here. So do I have a 5th power? I do. I have 2, 4, 5. There it is, 5th power. So that, my friends, is section 5.3, and that finishes the unit for us. We'll be talking more about the review and test, and I hope you have a great day. See ya.